Try to daw, Ade. Okay na?
Okay na.
Sige. So, matikang ako, matikang.
Kapitangan.
So, we proceed to synthesis of epoxides. Peroxy acid epoxidation. Peroxy acids, sometimes called peroxides, are used to convert alkenes to epoxides. If the reactions takes place in aqueous acid, the epoxide opens to a glycol. Therefore, to make an epoxide, we avoid strong acids. Because of its desirable solubility properties, metachloroperoxybenzoic acid, or MCPBA, is often used for these epoxidations. MCPBA is a weakly acidic peroxy acid that is soluble in a protic solvent such as CH2, Cl2. So, in this picture, you can see that alkane in which it combines with peroxy acid to convert it to epoxide. The peroxy acid is a functional group which is like a carboxylic acid but has two oxygen atoms. So it is like carboxylic acid that has carbonyl functional group, but it has peroxide instead of hydroxyl. Hydroxyl group has only one oxygen and hydrogen, which is OH, while peroxide group has two oxygen connects with by a single bond. So peroxy acid is what it looks like in the picture below. So when the alkene and peroxy acid reacts, it converts to epoxide, which shown in the picture. The example below is a cyclohexane that will explain in the next slide. However, MCPBA looks like in the next to the example. Next slide, please. The epoxidation takes place in one step, concerted reaction that maintains the stereochemistry of any substituents on the double bond. In this picture, it is a benzoic ring, which is a cyclohexane. This both picture is the same but different structure. Let's have an example instead in order for you to understand. Next slide, please. Cis-2-butene. The key to recognize here is the CO3H because CO2H is a carboxylic acid and CO3H is peroxy acid because it has extra oxygen atom. In order for you all to understand the example, I drew it in different colors so that you would understand that every atom and set of electrons. First, make the structure, then set the alkane over the oxygen of the hydrogen so that it is ready to react with a pi bond. So in here, the brown arrow is responsible of orange atom, and at the same time, the orange atom is going to use one of its own pair, which is in the orange atom, to attack the carbon atom. The left carbon atom is positive charge. That's why the oxygen attacks on it. So while the orange atom is busy with the alkene, the pink pi bond here between two oxygen atoms breaking away from the orange oxygen and attacking onto brown oxygen. But instead of staying on the brown oxygen, it moves to dark blue pi bond to form bond between carbon and oxygen. Now that the red carbon has two mating bonds, we have to break the double bond on the other side. On the other side, here in the CO that has red ball pen, and form a bond that connects to red oxygen to blue hydrogen atom. As for the result, it can be seen in the picture. Next slide, please. The peroxy acid epoxidation is quite general with electron-rich double bonds reacting fastest. The following reactions are difficult transformation made possible by this selective stereospecific epoxidation procedure. The second example uses magnesium monoperoxyphthalate, a relatively stable water-soluble peroxy acid often used in large-scale epoxidation. This aqueous MMP epoxidation carried out at neutral pH to avoid opening the epoxide and avoid the large-scale use of hazardous chlorinated solvents. You can see the example in E to nitro 1 phenyl propane that is now converted to E2 methyl 2 nitro 3 phenyl sorate. Next slide, please. So let's move on to base-promoted cyclization of halohydrines. A second synthesis of epoxides and other cyclic ethers involves a variation of the Williamson ether synthesis. If an alkoxide ion and a halogen atom are located in the same molecule, the alkoxide may displace a halide ion and form a ring. Treatment of halohydrin with base leads to an epoxide through this internal effect. So in this part, where you can see is a halohydrin. And the base here is the alcohol in which it interacts and takes the hydrogen because it is acidic. So here the oxygen base takes the hydrogen and forming a lone pair here in the oxygen that is located on the halohydrins. This will result to alkoxide ion, which you can see after back and forth arrow. So as you can see, once the alkoxide ion form, we have an interaction to alkyl halide. An alkyl halide is where you can see the X. So in this case, intermolecular will happen in here and ends it attack. So in here, the oxygen will attacks on carbon. So as it is elaborated by arrow in the picture, and attacks on X minus and will kick out. So that can be resolved to cyclic ether. This reaction is used to prepare a cyclic ether. So halogens on treatment with base will give cyclic ether. Next slide, please. So, hydrohydrins are easily generated by treating alkenes with aqueous solutions of halogens. Bromine water and chlorine water add across double bonds with Markov-Nikov orientation. The following reaction shows cyclopentane reacting with chlorine water to give the chlorohydrin treatment of the chlorohydrin with aqueous sodium hydroxides gives the epoxide. So here in the picture, a formation of chlorohydrin, the pi bond arrow will interact with chlorine in such a way that one of these chlorine atoms will now be on the molecule. This one chlorine will kick out and will result to chloronium ion. So in this part, we will have SN2 attack in which the water or H2O will attack along the way to chloride ion and will open it. That will result to transchlorohydrin. in displacement of chlorohydrin is we will have the minus OH attack along the way to oxygen inside here and will kick out. So it will result alkoxide. The reactions can be seen in here and will kick out the chlorine and that will form epoxide. Next slide, please. In here, this reaction can be used to synthesize cyclic ethers with larger rings. The difficulty lies in preventing the base added to the protonate, the alcohol, from attacking and displacing the halide. To 6-lutidine, a bulky base that cannot easily attack a carbon atom, can deprotonate the hydroxyl group to give a 5-membered cyclic ethers. 5, 6, and 7-membered, and occasionally 4-membered cyclic ethers are formed this way. So, in this picture, the one that is encircled is the 2,6-lutidine. Next slide, please. Acid catalyzed ring opening of epoxide. Next slide. The mechanism of this hydrolysis involves protonation of oxygen, forming a good leaving group followed by SN2 attacked by water. Anti-stereochemistry results from backside attack of water on the protonated epoxides. Next slide, please. So the mechanism of acid catalyzed opening of epoxides in water is this. Is we can see in this picture. Epoxides open the acidic solutions to form glycols. So step 1, protonation of the epoxide to form strong electrophile. So in this picture, the oxygen lone pairs that are tied in the cyclopentane will form a bond with that hydrogen and the oxygen, and this will result that the hydrogen form a bond with the oxygen, this one. So step 2, water attacks and opens the ring. So because the H3O plus or conjugate acid of water are now H2O, which is water, it will attack along the way to the oxygen and open the ring. So step 3, deprotonation to give diol. The deprotonation to give the diol, the water will again attack the hydrogen along the way to oxygen. That is bonded now to carbon here. So that will be the result of transcyclopentane 1,2-diol. Next. So, direct anti-hydroxylations of so next slide. So in alcohols, when the acid catalyzed opening of an epoxide takes place with an alcohol as the solvent, a molecule of alcohol acts as the nucleophile. This reaction produces an alkoxy alcohol with anti-stereochemistry. This is an excellent method for making compounds with ether and alcohol functional groups on adjacent carbon atoms. For example, the acid catalyzed opening of 1,2-epoxycyclopentane in methanol solution trans to methoxycyclopentanol. Look at the example in the next slide. So, mechanism of acid catalyzed opening of an epoxide in an alcohol solution. These mechanism steps are like the acid catalyzed opening of an epoxide in alcohol solution. So we will so the oxygen lone pairs inside this cyclopentane. The H plus is the acid, and the lone pairs will attack the acid, and that will form a bond here in the H, the oxygen positive, the oxygen positive. So step 2, the alcohol solvent attacks the opens the ring. So the in here the yung itong blue ano yun, CH3OH is will attack the O along the way to oxygen positive and will open the rings. So this will be the result. Yes. So step 3, deprotonation to give the product to alkoxy alcohol. So next slide, please. So using hydrohalic acids, when an epoxide reacts with a hydrohalic acid, a halide ion attacks the protonated epoxide. This reaction is analogous to the cleavage of ethers by HBr or HI. The halohydrin here initially reacts further with HX to give 1,2-dila halide. This is rarely a useful synthetic reaction because the 1,2-dila halide can be made directly from the alkane by electrophilic addition of X2. So next slide, please. Steroid, the opening of squalene to the epoxides is steroids are tetracyclic compounds that serve a wide variety of biological function, including hormones, emulsifiers, and membrane components. The biosynthesis of steroids is believed to involve an acid-catalyzed opening of squalene 2,3 epoxide. So the enzyme squalene epoxidase here, which opens and forms a carbocation that cyclizes under the control of another enzyme. The cyclized intermediate rearranges to lanosterol, which is converted to cholesterol and other steroids. Although cyclization of squalene to epoxide is controlled by an enzyme, its mechanism is similar to the acid-catalyzed opening of other epoxides. The epoxide oxygen becomes protonated and is attacked by nucleophile. So in this case, the nucleophile is a pi bond. The initial result is a tertiary carbocation. This initial carbocation is attacked by another double bond, leading to formation of another ring and another tertiary carbocation. A repetition of this process leads to the cyclized intermediate shown in this picture. Note that this sequence of steps converts an achiral, a cyclic starting material, into a compound with 4 rings and 7 asymmetric carbon atoms. The enzyme catalyzed sequence takes place with high yields and complete stereospecificity, providing a striking example of asymmetric induction in a biological system. So, next slide, please. So, base catalyzed ring opening epoxides. So, most ethers do not undergo nucleophilic substitution. Next slide, please. So, most ethers do not undergo nucleophilic substitutions or eliminations under basic conditions because an alkoxide ion is a living group. Epoxides have about 105 kJ per mole of ring strain that is released upon ring opening. However, and this strain is enough to compensate for the poor alkoxide living group. In this picture, it compares the energy profiles for nucleophilic attack on an ether and on an epoxide. The starting epoxide is about 105 kJ per mole, higher in energy than the ether, and its displacement has a lower activation energy. Next slide, please. The reaction of an epoxide with hydroxide ion leads to the same product as the acid catalyzed opening of epoxide, a 1,2-diol glycol, with anti-stereochemistry. In fact, either the acid catalyzed or base catalyzed reaction may be used to open epoxide. But the acid catalyzed reaction takes place under milder condition, unless there is an acid-sensitive functional group presentation, the acid-catalyzed hydrolysis is preferred. The strong bases and nucleophiles do not attack and cleave most ethers. Epoxides are more reactive, however, because opening the epoxides relieves the strain of three-membered ring. Strong bases can attack and open epoxides, even though the leaving group is an alkoxide. So the step 1 is a strong base attacks and open the rings to alkoxide. The step 2 is protonation of alkoxides gives the diol. Next slide, please. Like hydroxide, alkoxide ions reacts with epoxides to form ring open products. For example, cyclopentane oxides reacts with sodium methoxide in methanol to give the same trans 2 methoxycyclopentanol produced in the acid catalyzed opening in methanol. So next slide, please. Next slide. Amines can also open epoxides. Ethylene oxide ethylene oxide reacts with aqueous ammonia to give ethanolamine, an important industrial reagent. The nitrogen atom in ethanolamine is still nucleophilic, and ethanolamine can react further to give the ethanolamine and to 3-ethanolamine. So good yields of ethanolamine are achieved by using excess ammonia. So that's all.
So next is the orientation of epoxide ring. Uh, to further explain what is acid-catalyzed and base-catalyzed epoxide opening, we first define what epoxides are. So basically, epoxides are type of cyclic ethers. They can undergo both acid and base openings. Epoxides are actually some sort of organic structure that is a three-membered ring, and at the top of it is an oxygen. So here is a example of a structure of epoxides, where R there is another atom or another molecule na naka-attach. So next slide, please. In acid-catalyzed epoxide opening, the acid is catalyst. It means that it should always regenerate itself at the end of a reaction, or in other words, we should be able to get it back. So it says here that if only primary or secondary site is present, SN2-like behavior takes hold and less substituted site is favored during attack. So let us explain this in a simplest way. So next slide, please. Example hining a structure. So we can see that it aton left na carbon is secondary, yeah, and an aton right is primary. So next slide, please. So here, we can see that another structure, nag-react hiya acid na HCl. Yan na, our epoxide or the oxygen will grab a acidic hydrogen. So, ang usa nga lone pair ha oxygen, mababalhin na chlorine, and ang hydrogen na chlorine, mababalhin na di oxygen. Ini nga process nahihimo hiya para maging ready for opening. It opening meaning is pag-break ito nga triangle ha aton structure. So next slide, please. So here we can see an outcome han pag-grab han aton epoxide han acidic hydrogen. So yan na ready na hiya for opening with the chloride. So the question is hain ma-attack ang aton chloride. The chloride will attack to the left hindered position or less substituted, which is basically means adiya ma-attack ka CH2 kay na amo it aton primary carbon. Mas less hindered man it primary kaysa secondary kay obviously mas gurugot it 1 kaysa 2. So next slide please. So in here we can see that ang process han pag-attack kan usa ka lone pair ha chlorine ngadtohan aton less hindered position. Yan akong ma-observe niyo an arrow nga daigbaw or nga dahan between han C ngan han O is dida nag-indicate nga dida mahihinabo ang aton opening. So next slide please. So here this will now be our expected product. So observe ka mo nga na-break na naton ang triangle structure, dito aton structure, tas ang aton chlorine naka-attach siya CH2 kay dito siya nag-attack kanina. So next slide please. It also says here that if a tertiary site is present, SN1-like behavior dominates and a strong partial positive carbocation will build up for attack. For example, Ini nga structure same laya kanina. So ang natong process na liwat nga natong epoxide or ang natong oxygen ma-grabhin acidic hydrogen o siya mababalin niya ngadto ha oxygen yan ang usa nga long pair ha oxygen mababalin niya diha fluorine. Pero yan ang ma-observe niyo nga ang atong left carbon is tertiary na hiya. As siya, kung mapapansin niyo nga diha right part hit aton picture is an atom chloride nag-attack siya nga to tertiary carbon or tertiary site which is an atom last na carbon because in tertiary site you have greater hyperconjugation and you've got the ability to host partially positive carbocation and build up to a better degree. So di ba kanina napansin naton ang aton example kanina ang present la kasi is secondary and primary site. So kung ito lang nga duha it present ang iga-attack kita itong reactant is an mas less hindered, which is an primary. Pero pag present na it tertiary, iyan na iga-attack is an tertiary na. May dagya pa kito dida na ngalimtan ngayon niya. Between heat, carbon, and oxygen, may arrow na lat dida, which is ma-indicate na lot nga dida naton masasabtan an opening. So next slide, please. So this will now be our expected product. So as you can see, ang atong fluorine naka-attach sa second carbon which is amo itong atong tertiary carbon kanina kay di dahiya nag-attack or di dahiya ma-attach. Tapos napansin gyud niyo nga na-break na naton ang triangle nito naton structure. So always remember lang na pag acid catalyzed opening, I mean epoxide opening, pag present la is secondary or ngan primary site, aatakaton reactant is an less hindered or an primary. Pero pag present and tertiary, ang reaction kuan aton reactant is an tertiary. So now we will now move on to base catalyzed epoxide ring opening. So something that epoxide ring can undergo that regular ethers cannot is base catalyzed reactions. All ethers can react with acids, however, epoxides specifically are able to react with base. So unlike acid catalyzed, base catalyzed epoxide opening is exclusively SN2 in nature. In other words, we will always be headed towards the less substituted area. So example here, let's focus first sa left side ng picture. As you can see, an aton structure nag-react kiya base na hydroxide which is an ada igbaw and ang water ada ubos. So kung mapansin niyo nga the right side nga picture, ang aton usa ka lone pair nga hydroxide will act as a nucleophile and will attack the less hindered position which is an CH2 kay amo naton primary carbon. Kanya naging primary kay ma-observe niyo nga naka-attach siya nga dahil last na carbon which is usa ka carbon at naka-attach siya iya. While ito nga last na carbon, naka-attach siya tulo nga dahil igbaw ubos nan ito nga CH2. So obviously, ang CH2 amo ang aton less hindered position. So yan na ito na lot na arrow haigbaw between haungan na C na indicate na di naman na nabuan naton opening. So next slide please. So here, pansin niyo nga ang atong OH or an atong hydroxide naka-attach na iya CH2. Actually, may nangalimtan na liwat ako. O nga nit C, may dapat itiya line bida, dapat naka dugtong ito hera. So, dili nga masulod ang aton water or ang aton H2O. Kaya mabalik ito ha process nga ang aton epoxide or an oxygen makuha hiya hin acidic hydrogen. So, mababalhin na liwatan usa ka H2O nga diha oxygen yan usa nga lone pair hydrogen mababalhin nga nahiya nga diha OH. So, asya tiya naging negative OH. So, next please. So this will now be our expected product. So remember lang in base catalyzed epoxide opening, it reactant ma-attack hiya permi less hindered position regardless kung may diya tertiary site. Unlike kanina natin acid, pag may tertiary site hiya, um, it attack it reactant ngadto hit tertiary. Dinhi bisan may da tertiary, ma-attack lagi siya ha, less hindered position. So, may dalat kita tinatawag nga Grignard reagent. Next slide, please. In here, we are going to have a magnesium halide reagent. And when we use that, it's going to create a strong alkyl base. For example, in yung structure, actually same lang ang structure na gamit kanina para di rin na malipat. So, as you can observe, dinhi may daduha ka steps which indicates numbers 1 and 2. So, has step 1, amoy create atom Grignard reagent which has a partially negative and partially positive. And step 2, an adaobos, amoy create atom acidic wash. Again, Grignard reagent is a base, so it will always be a base opening. So, next slide, please. So, here, pansin niyo na ang aton CH3 or an aton alkyl group aton reactant will act as a base kay amit aton negatively charged and react is less hindered position as siya ito nga CH2. Tapos ito nga aron nga kaigbaw na indicate nga di daman na nabuan aton opening. So next slide please. So dito makikita na naton nga ang aton CH3 which is pinakalas nga CH3 nag-attach niya CH2. Actually diri pa ni naton final product. Next slide amot aton final product. So this will diri pa ni final product ngayon. I'm sorry. Second step pa lang ngayon ni Hiya. Kanina ngayon first step pa lang to. Di din na masulod ang aton H3O+ na nakadiha ubos. Kay mabalik na lot kita ha. Ang kanina ini nga slide, ito nga slide, actually dapat may dapat iya triangle ha, ito nga structure, nalipat na liwat ako. And did, next slide. Did, ang process natin makikita, pag-open aton epoxide ring. So, dili mabalik na lot kita nga aton epoxide or oxygen, magkuhahin acidic hydrogen, nga mababalin niya nga diha oxygen sa lone pair oxygen mababalin liwat hiya nga dihan aton OH+. And next slide please. This will now be our expected product. So napansin niyo nga ang pinagkaibahan nila kanina is ang aton O yan may dan na hiya H. So, ito tanan an explanation about an acid catalyzed epoxide ring opening and an base catalyzed epoxide ring opening. So, last topic will be epoxy resins. Next slide, please. So, epoxy resin simply means unglue or unpaste natin yung gagamit nowadays panpadikit. But to elaborate more about epoxies, they are bonded by ether linkages, so they are unaffected by water. Epoxies uses prepolymer that can be made as runny or as gummy as desired, and they use a hardening agent that can be modified to control the curing time. But with the absence of hardening agent, they have a long shelf life. So the most common epoxy resins uses a prepolymer made from bisphenol A and epichlorohydrin. So at other picture, may example, also dito example, amo talaga get structure hit bisphenol A or BPA nga hit epichlorohydrin. So next slide please. Alaigbo picture explains that under base catalyzed conditions, the anion of bisphenol A opens the epoxide of epichlorohydrin to give an alkoxide that snaps shut on the other and forming another epoxide. This second epoxide, which is an adiabuso picture, reacts with another molecule of bisphenol A, and each molecule of bisphenol A can also react with two molecules of epichlorohydrin. with exactly equal amounts of bisphenol A and epichlorohydrin, this polymerization would continue until the polymer chains were very long and the material would be a solid polymer. In making epoxy resins, excess epichlorohydrin is added to form short chains with epichlorohydrins on both ends. More epichlorohydrin gives shorter chains and a runiper polymer, while less epichlorohydrin gives longer chains and a more viscous polymer. So that sums up our reporting. Thank you for listening.